Okay, year 13. This is the final part of the radioactivity and nuclear power area of the course. This is the stuff that you've been doing your research on, so I'm going to just do a quick run through. It's about making the links to the basic ideas from other parts of the course. So nothing particularly new here, but quite descriptive, and it's about what goes into the descriptions that's kind of key to it. So I'm going to put the two last parts together because it's not too tricky, but it's the idea that you can't have one really without the other. So if we go to where we are, last section, let's move away from the ideas of forces and fission and fusion. This could happen in either type of reaction. At the moment we are not in the stage of having nuclear fusion, so these are all fission reactors. So first things first, quick run through. Some of this is not necessarily as you think, and that's the only slight tweak to it. Other than that, it is a thermal power station. It's just the same as normal, as you did at GCSE. You will have some source of energy, some source of heat. It is producing heat that is then taken to, under pressure, to a set of fans, which are your turbines, and those turbines then turn that into mechanical energy. They're actually causing work done to make things move, and therefore your alternator stroke generator, you're going to induce electricity. So all of that end, all of the right hand end, is what we studied really in the principles with magnetism. This bit is kind of more straightforward. You could think of this as a kettle, and the steam coming from the kettle blows your fans over here. Now, a few little thoughts to go around with it, where we bring these things in, but other than that, fairly straightforward. So, UK and worldwide, the vast majority of power stations fall into two groups. They're either pressurized water reactors or they're advanced gas-cooled reactors. Okay, we have other types, fast breeders. They use slightly different fuels, they use slightly different materials in their moderator and control rods and so on, but the principle is the same. Okay, we have a fission reaction that is causing energy to be deposited in the right way into something which will then take that energy to the fans, to the turbines. So, been successful quite a few years. Let's just move that out of the way. So none of it is particularly clever, as I say. Fairly obviously you will have some sort of fuel, as you would in a coal or gas or other thermal power stations, but this one does not involve any burning. So one of the things you might notice that is probably most noticeable is that if you're looking at a nuclear reactor based power station, then it's very clean. There are no towers, chimneys, there's no chemical pollution given out, we're not poisoning the atmosphere, etc., through carbon dioxide and other effects, sulfur dioxide and so on. Obviously the big contentious issue is nuclear waste, but it's a completely different type of problem to the vast majority of power stations. Okay, this is quite a low carbon based system. We need to transport the fuel, but other than digging up and transporting the fuels from abroad, Australia, Russia, places like that, we use very little carbon dioxide. We're not burning anything. So key components as we go through. The main thing that we're going to use, and this is where you do need to remember those key bits, is we use mainly uranium-235. Okay, the most common type of uranium is 238, but it's a little bit unpredictable. Okay, so although less than 1% of it is uranium-235, it's that we want. Okay, so the reason we use that is because this is quite easy to fission, to split apart in a controlled way. Okay, so we try and enrich the fuel so that you end up with more 235 than you do the rest of it. Okay, so there's quite a lot of processing takes place before the fuel actually gets to the power station. So, I did give you an article on thorium-based reactors. Thorium is easy to get the fuel, so again, there's a lot of advantages to it. It also has less waste products, or the waste products can be then used again, so much more recycling going on. Okay, moderators. Let's go from that. The obvious thing is we got fuel. We have things that can be giving out energy. Okay, on their own, fuel 235, for example, uranium-235 has an extremely long half-life. So fuels are basically quite stable, and it's us humans that then induce them to do something, to release their energy. Okay, which makes them safer. We have to control the process. Now, what we'll do is we will, like we said in the last section with the chain reaction, is we'll add a neutron to the nucleus of the atoms. Okay, so we will have neutrons in there, and those will cause it to become unstable and then split into two parts, two halves roughly. That's your fission process, but it's induced reactions. It is not a natural spontaneous reaction, so we have to hit it in. Now the way to get the neutrons in is that we have to have them absorbed. When they split, they fire out more neutrons. That is your chain reaction. But if they're going too fast, effectively you collide at high speed into your nucleus. Neutrons can get knocked out the other side without splitting the nucleus. So you need to carefully get them the right speed so they're just absorbed. So moderators are things that are really good at absorbing neutrons, okay, but not keeping hold of them. So collisions happen, we don't take away the neutrons, we are just taking away most of their energy. So neutrons, when they released from a splitting of a uranium-235 nucleus, are pretty fast. Okay, so tens of millions of meters per second, and you want to slow them down to there about the speed of thermal things. I got down here around about a 40th of an electron volt. You know, really quite slow. Okay, so slower than air particles around us. So we need to take most of their kinetic energy away, and we do that by having inelastic collisions. Okay, so when they collide, when the neutrons collide with your moderator nuclei, so the big targets that are sat there blocking the progress, as the neutrons hit them, they're going to slow right down. And the way to do that is have the moderator absorb most of their energy. So the nuclei within the moderator bounce around. They'll absorb most of that energy. It's the moderator that gets hot. Okay, and it's the moderator that actually takes the energy, captures the energy, and then releases it for it to be used by the generation system. Okay, so moderator is really, really key. Twofold, I think, to get the heat, but also to do it by slowing them down so the process happens. Okay, so couple of key terms. Thermal neutrons are the main thing, so the whole idea of these slow moving particles around about the section of heat, but the other stuff is kind of pretty obvious other than this one clever thing. So we'll start off. The factors that affect the choice of materials we can use as moderators is we basically, the main thing that we want is that they are a small, or the atoms within them have a small low mass nucleus. Okay, and the reason is that's why it makes sense, so that collisions from the neutrons, those free neutrons that are flying around, are inelastic. I mean, if we go back to the work that we did last year on elastic and inelastic collisions, these are really inelastic. You know, most of the energy is taken out of the neutrons. So that's its main property that we want it to do. We want to do that without, most importantly, actually absorbing. Doesn't. So it doesn't absorb. So it lets it collide, but there's no room in each nuclei to actually keep hold of those neutrons. So only certain chemical materials will do that. Chemical elements and compounds will do that. So there's actually not much choice for moderators, to be fair. The other thing that's really, really important is it's absorbing most of the heat. So again, not genius, but it has to have a really high melting point. Okay, we don't want our moderator to melt if it's solid. Let's just put in if solid, or if it is liquid, we don't want it to boil, so high boiling point. Okay, now the things that work well for that actually are used mainly in the vast majority of reactors, around about 75% of the ones around the world, is water. Water is a really good material. It has a really high specific heat capacity, not much use for this, but it's actually quite hard to boil if you keep it pressurized. Okay, so we'll come back to the pressurized because actually that's no need for it here, but we can use water for one of the other uses as well. So it has two uses. So water is normal everyday water-ish. Actually, light water is what they'll often call. What they often call it, because they'll take away some of the naturally occurring deuterium. They actually want the really low mass normal H2O in there. So let's just put in brackets, as I say, large number, it's mainly water or graphite, which makes up about 20% of them. Okay, so carbon, small carbon, you know, it's carbon 12, it's quite a small nucleus, so it slows things down really, really well. Okay, so moderator's really important. What we actually want in terms of our get a picture back, our thing then is we end up with really hot moderators, which is surrounding, and this is the key bit, it's between all the nuclear materials, so that, you know, it's surrounding it so that any neutron shot off in any direction will be moderated. And then before they go on to the next piece of, or the next fuel rod, okay, next piece of fuel. But we then want that heat to be taken and used. So what we need is some sort of material which we call the coolant, because it is something that takes the energy, releases it, cools down, goes back, and we just recycle it round and round all the time. So the other key process that's kind of sat there in the background that you need to have all the time is you need this right material for the coolant. And again, it doesn't need to be genius. What we need is something, as I said there, to take it off to the heat exchanger. I'll come back to why on that in a second. And I said touches the pipe, but it's in contact with the pipes. So it can absorb as much energy as possible. As you want it to absorb as much energy as possible, it needs to have a high specific heat capacity. That is its main function. That's going to absorb a lot of energy without getting too hot, and therefore it can take that energy away and deliver it to where it's needed. Okay, so it doesn't matter, I should say it's a high specific heat capacity and it needs to be able to flow, so it has to be a fluid, liquid or a gas. As it goes around the pipes, kind of obvious. It also needs to be in the background of things, it needs to have a very high, high boiling point. Oops, excuse me, I can't spell. Boiling point. So two thermal properties it needs to have. It needs to not turn into a gas if it is a liquid, or it needs to be very dense, because then again we can squash it together and absorb a lot of energy. So the problems that go with this is that most things do boil off really quickly. Okay, water boils at only 100 degrees C. So what we need to do is we need to pressurize this. because if we squash water and keep it really highly pressured, there's nowhere for it to turn into a gas. Okay, again, it's back to the standard gas laws. Now, there has been a lot of pressure a lot of pushing to get sodium used, because sodium has a really high specific heat capacity. It melts at around about 900 degrees C, so you don't actually need to keep it under pressure, which is often safer as well, because if you are pressurizing everything, crushing it, then it's very easy for that to blow and pipes to split, and then you get a leak. Okay, so that's one thing they're talked about. So far, there's only a couple of power stations in Russia that that actually run on it, liquid sodium. But there's America's looking to actually have these in your local neighbourhoods. There's a lot of research into the possibility of using it. Yeah. One last point is it also needs to be very pure. Okay, for whatever you're using, and the reason is it's going to be in that self-contained system going around and around. You can't afford it to corrode any of the pipework, because you cannot get to the pipework. It needs to last the lifetime of the power station. Obviously bits of it you can, but the bit within the reactor you can't. Okay, so it needs to be very, very pure. Last thing worth pointing out, again, it's beyond the course, but again, it's a poor neutron absorber. Because if you absorb neutrons, if you start getting too many neutrons in your nuclei, they become unstable and they decay. They become radioactive. So to stay stable. Okay. So that's kind of an important one. Again, it's beyond the course, so I'll put that in brackets. But you know, you want to limit what you make radioactive in terms of waste. If you don't have to treat it as waste, then you want to avoid that, because there's storage problems, which we'll come to in a few minutes. So yeah, poor neutron absorber is good because it doesn't become radioactive. So what is a good material to use? Well, water. Okay, that's why we have the PWR reactors. Pressure prevents it boiling. It has a very high specific heat capacity. It's a great material for absorbing energy. Water, 4,200, 4,160 joules for every degree centigrade rise of a kilogram of water. But even better, excuse me, getting beeping in the corner, is that it not only acts as a coolant, but it acts as a moderator as well. So it's actually doing two roles, which means you can make your design of your reactor much simpler and smaller, more compact. The other type of reactors, the ones that aren't PWRs, are AGRs. So what they use is carbon dioxide, so CO2. Advanced gas-cooled reactors. So they are gases, again at high pressure, because then it's better, you have more neutrons within the same volume, therefore it's better at absorbing energy. Okay, so again, it increases the specific heat capacity because it's being kept under pressure. Something a little bit beyond our thermal that we did, but again, links in with Boyle's law. Okay, so maybe go back and revisit that, have a think about it, but again, beyond our course. So just go with the idea of kept under pressure. So those are our two main passive parts of our system. Yeah, our fuel rods, our fuel we put in. When they run out, then you need to replace them. But the moderator and the coolant are designed to try to keep them in as much as possible. Now, if they don't absorb neutrons, as we said here, then they won't become radioactive, so they will just keep their properties and you can keep them going for a long, long time. Okay? The rest does change. So the fuel rods, And the bits that control the reaction, the control rods, they make a big difference to what's going on. Okay, so what we've got going on in this final key component is that basically you need something to stop your power station becoming a bomb. And the thing that keeps the chain reaction going is the neutrons. So what we want to be able to do is take away some of the neutrons. Now, the key thing that really matters beyond this is that in our chain reaction picture last week, in section 2, the assumption was that all of the neutrons that come out will hit a nucleus of another uranium atom and therefore cause fission. That's not true. Yeah, they'll fire off in different directions. They might completely miss all the fuel rods that are in there. You try and optimize it, the design, so they're close enough together, but some will miss. So some neutrons are just lost. They'll hit the wall of the reactor, get absorbed into that, they're no use anymore. Okay, others might be just a little bit at the wrong speed, so they might just bounce off because they've not gone through the moderator, so they've not been slowed down, they've not been moderated. So real life is a bit more complicated, but on the assumption of all of them getting through anyway, we need to be able to absorb and take away some of those neutrons that are coming out. Okay, so the key point I wanted to link again is on average 2.5, which you can't obviously get, so 2 or 3 neutrons are released for every fission. So that could increase the size of your reaction, the rate of your reaction, by 2 or 3 times each second. Yeah, so it's a runaway effect. So we need to take away, we need to literally remove some of the extra neutrons. So if we can get something, we need something that's really good at absorbing them. Okay? Now, there's nothing clever about this as such. If you get the right material, it works. If you have too much of the material, too much surface area, then it absorbs too many of them. Okay, so if you take away too many neutrons, the chain reaction gets smaller and will eventually close itself down. Okay, so what we have are control rods that are raised and lowered in the machine within the reactor itself. If I just bring my picture back, which I've got on walkabout with, here we go, slightly different picture. Yeah, these are lowered in and out between the fuel rods and moderators, so that as the neutrons fly around within the pressure vessel, within the reactor itself, some of them are stopped on the way, some of them are absorbed by the control rods. Okay, and in the UK and most power stations around the world now, these all come in from the top. In Chernobyl, they were using a design that was based on nuclear submarines, where you can't use that system, and they came in from the side, which has a real issue with safety, as we saw. So, control rods lower down from the top, absorbing the neutrons, therefore preventing the process from taking place. Okay, you are sucking away the things that actually cause the effect to happen. So that will further reduce the amount of fission. That's the key point with it all. Okay, so what do we need? Well, again, we need control rods that do not fall apart. So they need to be very tough, they need to be very dense. So again, in Chernobyl, if you've read the book, it gives you a bit more detail, quite a lot more detail than the films do, than the film series did. The tips that they had on them to make them tougher was actually something that sped up the reaction. Okay, it didn't absorb neutrons, so the material itself needs to be dense and tough all the way down. It needs to be good at being hit, basically. It needs to be solid, so you can't use liquids with this because you need to pull them in and out. So it needs to have a very high, again because it's in the reactor, so everything in the reactor needs to have a high melting point if it's solid. Okay, And then the key thing is it is very good at absorbing, again it's not geniuses, absorbing neutrons. Okay, but crucially absorbing neutrons without becoming unstable, because if they start becoming radioactive, then you need to get rid of them. They also, if they're reactive, if you have things that are naturally radioactive inside the reactor, okay, just think of that, materials that aren't going to decay normally, they're unpredictable, you don't want them in a reactor that you want complete predictability for. So they have to be good at absorbing neutrons without becoming unstable. Okay, you need to keep things from becoming radioactive. So various materials, indium and silver. Most things are actually an alloy of silver, indium and cadmium, but again generally the main materials in the earlier days, where it's more straightforward with simpler fuels. Boron is a good one. Boron is boring, it slows down the reaction. That's how I kind of keep it in my head. So yeah, control, all about being boring. And cadmium, which is the name of a small town near where I lived as a child. So again, it kind of sticks in my head. But yeah, boron and cadmium. It's quite a boring town as well. So those are the 4 parts that you need to know your way around. Okay, you need to make sure that you keep those handy and clear in your head how they link together, and say if you can kind of visualize it, then that really helps. But the pressurizer, the heat exchanger, and the pump, all of these are key components as well. All we're just looking at is the kind of process that links in with the reaction here. Okay, the induced reaction that we have made happen because we have fuel rods in. Now, if anyone's kind of saying, well, where do neutrons come from in the first place? I'm not sure at the very beginning, but you always have some fuel rods decaying away or being split within the atom. Within the reactor itself. When you're changing fuel rods, you don't empty the whole thing. Okay, so you're kind of keeping it going. The pressurizer, fairly obvious I think now, so that you can actually keep a higher density of fluid in there. And the other thing that's really important is the heat exchanger. You're outside of your control shielding around the reactor, the concrete shell that's around the actual steel reactor itself. That's obviously there to shield you from radiation. All the main stuff that needs fixing and moving parts, etc., all of that tends to be elsewhere. So you want non-radioactive materials flowing out of this area. So what we have is a sealed circuit where we have our radioactive coolant, or our coolant is taking stuff through. We will get perhaps a little bit of decontamination, contaminants coming in. So you're going to get contaminants that kind of floating around. So just like you do in a normal radiator in a house, sludge starts flowing a little bit. And that's as it goes around. Again, you don't want it to go through. So this is completely sealed off, and lots of surface area for the hot coolant to then pass on via conduction to the surrounding coolant, which then is free to go off without being contaminated. Okay, so heat exchangers are important components in this stage. They're not necessarily as important in other thermal power stations, although they do prevent corrosion if you keep it sealed. So again, it's slightly better. But if you know your 4 parts, the fuel is fairly obvious, but there's a little bit of detail. Uranium-235, not 238, enriched to make more of it in the fuel rods. Okay, so key word there. You've got the moderator to give you your thermal neutrons. Okay, how do they do that? By taking away their kinetic energy. You've got your coolant, which has to be specific heat capacity, a high specific heat capacity, and then your key thing about the control rods is that they are, just get it in, there we go, they are controlling it by absorbing neutrons but without becoming unstable. Okay, so those are kind of key components. Let's just star that one, and let's just star the specific heat capacity. Okay, those are kind of key properties of them. Now, if we just move on to the safety aspects, you can't really have one without the other. A lot of it's fairly straightforward and kind of obvious. A lot of it is very similar to what we did with the practicals. Okay, shielding, getting distance, things like that. However, how we treat the waste depends on what type of waste it is, and it really comes down to the two kind of key things. Is it something that has been contaminated? There has been some spills, you know, a lot of students contaminate my room by dropping liquids and things. That's just simple contamination. But if it's a radioactive source, if there is some radioactive nuclei that have been there, then that thing itself is now got radiation in. Okay, it may not be radioactive, but it has radiation that you cannot find in it. In the early days at Doon Ray, which is a very experimental in its time up on the north coast of Scotland, they ended up having to they got a contamination within a minibus. So the minibus then became radioactive ever so slightly, as in you had this fuel that couldn't be tracked down, this contaminant that was radioactive, so they just buried the whole bus. Okay, it's so not all new radioactive nuclear waste is bad. Some of it is actually really minimal. When we get rid of our sources, I have to do exactly the same thing. So even though they're relatively safe, we need to get rid in a certain way. Things that have been irradiated, well, again, irradiation causes problems for living tissue. So things that have been irradiated, unlikely to be much of a problem unless they have absorbed neutrons. So if they were in that reactor, things that are surrounding, so not in the reactor itself, but in the reactor building, then those things have to be treated depending on their likelihood of radioactivity. So the casing around the reactor needs to be nice and strong, obviously, needs to hold shape and so on. So this is often steel. The steel is also being bombarded by neutrons. So the steel liner will become radioactive over time. Okay, again, carefully chosen in a way that tries to limit that, but the concrete around it, which prevents radiation reaching us, the emissions reaching us, that over time becomes more unstable. Okay, and there's a big mass of it, so it's not highly unstable, but it will become radioactive, and that's usually when nuclear power stations are decommissioned and the building itself of the reactor building, that is, will be radioactive. So just near the Severn Bridge, if you're driving down the M5, just before you get to the bridge across to Wales from Bristol, you'll see the old power station there, and the reactor building is still there. It's the only thing, and it is just completely sealed off, waiting for it to decay in terms of its radioactivity, its half-life to drop enough for them to unseal it and deal with it in a certain way. Okay, so that's our kind of key components of it. Is it contaminated? Is it a fuel, for example, but is it contaminated as well? Or is it just being irradiated? So again, need to kind of make sure you're happy with that in your head. Okay, safety considerations before we get to the waste. There's some fairly obvious stuff. Use solid fuel rods rather than a liquid, unstable, uranium liquid, for example, or thorium liquid, because it's easy to spill liquids. So solids, much easier to not spill. The shielding, okay, again, steel and concrete. Again, they need to stand high pressures, but not as high, except around the actual reactor itself, around the core. etc., etc. So fairly obvious, preventing people going nearby. So all this kind of stuff. And then the bits that weren't in place with the Russian power supplies originally, I know it's in Ukraine, but it was a Russian Confederate at the time, part of USSR. We have much safer systems than they do in terms of the actual engineering and science of it. So if you have something that's going wrong, temperature's going too high, whatever it is, automatically controlled all the time, you need to cool the reactor immediately. What they'll do is they'll just drop the control rods in. Okay, so if it's an absolute emergency, they'll drop them in, but they'll actually just usually control them and just lower them in. So that's our main default thing. Now that absorbs the neutrons, that can stop the entire reaction taking place, the chain reaction taking place. Okay, so that's one of our main things. Again, if there is a backup power supply, for example, and we can't roll them in, well, you have an electromagnet that keeps the whole process there. So if the electricity cuts out, they literally drop into the core and stop it immediately. Okay, if there's a leak in the pipe, so the pressurized water system, for example, so round here, then what we have is safety systems that will inject coolants directly into this water, nitrogen, things like that. So basically acting like a fire extinguisher. So there's some emergency shutdown procedures. Again, all this is kind of background logic really. But the bit that matters based on these is what do we do with the waste, as everyone is the thing that people talk about. So 3 levels: high level, medium level and low level. Okay, so that's our kind of process. The high level radioactive waste is the stuff that is still radioactive. Okay, so this is basically the fuel rods. So the uranium breaks down, it splits. So you did have, I don't know, 1 million uranium-235s. In theory, if you used it all up, you'd end up with 2 million smaller nuclei. Okay, so all the protons and neutrons are still there, but they're now split into 2. So actually you've got more atoms than you did. Now what we tend to do is we'll take it out much earlier than when we have to use them all up, because you need neutrons to come and hit a uranium atom. If there's not many uranium atoms left in your fuel rods, if that's your fuel rod and you've got a bit of uranium down here and a bit up here, there's a fair chance they're not going to get hit. So it just doesn't work. Your reactor will stop giving you energy, stop releasing energy. So when they are depleted, okay, again, keyword, depleted, when they're no longer as unstable or ready to be induced as they were, they need to get rid of them. So they'll take the fuel rods out. So it's quite a regular process. And again, like the photos I showed you with the thing that irradiated the bandages, what they'll do is they'll just be a continuous process of changing a rod every now and then, a bit like painting the Severn Bridge. You start one end, and when you reach the other, you start again at the first end. Okay, so you just go round, changing everything slowly. When they're taken out, if you think about what we just said, they are radioactive still, or ready to be radioactive. Be a little bit careful there, they're not naturally radioactive, but the products can be. So if it splits into strontium and whatever, the strontium and it's the other daughter nucleus could be radioactive. There's a fair chance that they are. They're not going to land perfectly on the stable line if we go down that proton-neutron graph. So the chances are the daughters are radioactive. Because they're radioactive, they don't last for long, usually, because they're smaller. They'll be beta emitters, beta plus, beta minus. So they're not radioactive for very long. So we just need to store them away safely while that decay drops down. The half-life gets smaller and smaller, or not the half-life, but the activity of them over the half-life gets smaller and smaller and smaller. We can store them away. They're also, of course, very hot, so we need to put them into tanks to cool them down. So they're called cooling ponds. you know, nice obvious name. But as I said there, it's mainly to let the radioactivity die away from the daughter products and contaminants, because don't forget, fuel rods might not be pure uranium-235. It could have other elements within it. It's then processed. Okay, and what they'll do is after they'll process it, it'll still potentially be quite warm. The robots I use to do this is not, it's an automatic process, it's not people. Still going to be pretty hot. They'll encase it, and again they'll put it back into storage tanks. So this is not on site. Usually, this is usually somewhere else. I think there's only one place. Most of our waste in this country goes up to what used to be called Windscale, now Sellafield, out on the west coast of Cumbria, and there is a power station there, but it's mainly a processing plant. Okay, so it's transported there. When it's cool enough, what they'll do is they'll remove the cladding. So there'll often be an alloy surrounding the fuel rods with cooling fins and so on to make it more effective. And what they'll do is they'll separate them out into anything that is unused. So this is the processing. Okay, I haven't actually put that in that sentence. Processing involves this. And then they'll get, other fuel is potentially available. So maybe you've made plutonium on the way, again can be used. And split off the radioactive waste, which is highly ionizing. So that's your split, okay? What you want and what you need to get rid of. You can seal the fuel for, again, building back in, using in enrichment, using as a future fuel and so on, making into future fuel rods. And the waste is usually then got away with in a way that is going to be sealed. Okay, now often it's quite a small amount. I should say this is actually about the size of a fuel rod. Okay, pens perhaps a little bit fatter. There we go. That's about the size of a fuel rod. Again, I've used when I went to Euroways, they had a depleted one on the desk of the boss, and they're about twice as long as that. And what you'll have do is like one of those pens where you just used to put loads of leads in. You just fill it up with these rods. They'll take out the entire casing, and they'll basically take out the ones that are still useful and so on. So they're quite small. And what they'll do is they'll take that rod and usually vitrify it. They'll seal it in glass. And the reason they seal it is because it then can't react, because it's with other surrounding materials, so chemically reacts because it's sealed away in glass. And it's also sealed off so it can't give out that radiation in quite the same way as well. So lastly, most importantly, is it prevents, although it's the same concept, it prevents water getting into it. Because if you put it sealed up in a container deep underground, that's not so much to keep it away from people for the radiation, but actually just because people can't then get into it and wander around and poke things around and so on. They'll seal them up in containers that are kept cool, so keep pumping air through to keep them cool, to cool them down, because they'll still be warm. And obviously if you seal a container and it's warm, it'll expand and potentially explode. And they'll put it somewhere stable where the cave system's not going to be collapsing. So mines are very, nice deep holes in the ground are good, but usually in granite areas where they don't split or where there's any chance of volcanic activity, and crucially, not dripping in water, because water is a moderator, and water can help that then cause reactions to happen. So you don't want that for fairly obvious problems. Okay, so what's this whole process? You're going to cool it in water for a few months, for 6 to 9 months. Okay, that kind of length of time. It's nothing, it's not years. Okay, then process it or reprocess it. And return to the water as it says above, but for a longer time, for 1 to 2 years. Okay, when cool, they'll store it, as I say, underground, sealed from water. The vitrification and the drums and everything else, sealed from water. In a mine for hundreds of years. Intermediate waste is the stuff they've stripped off the fuel. Okay, so the element cladding, as I said, the sludge from actually within the processes, within the water tanks, the sludge builds up, wherever you can have potential waste, but again, it tends to be radioactive rather than the fuel itself. But don't forget, this also includes not just nuclear reactor power stations, but also things like stuff we use in school and stronger stuff that they'll use in hospitals and so on. Okay, so all kinds of radioactive materials, they need to be stored in another way. They're not as dangerous for as long. Okay, so the crucial bit is they need to be below a certain dose to qualify as intermediate levels. So 12 million becquerels per ton for most radiation, but because alpha is more ionizing, causes more damage, 4 becquerels, a gigabecquerels or less for alpha. Okay, this one again, when it's cool, sealed away, encased, just again deep underground, often because it's a convenient place. We have a lot of mines where it's stable, low water flow, etc., etc. But what they'll do is this one, they'll just store it for hundreds, well, tens to hundreds of years. Okay, so usually hundreds because it is radioactive, but again, after cooling in the ponds. Okay. Low level waste can be all kinds of things. It could be your paper suits, it could be your jacket, it could be the masks, the bulky stuff that is used. It could be a minibus, that kind of thing. Whatever it is, the water itself needs to be treated as well. So, they will process as much as they can to obviously be as efficient with the cost as they can. But this is really low level stuff. This is the kind of levels that we were kind of working at with our lab, in some of our lab sessions. So again, sealed, buried, not very long. Buried, when I say, is it's not buried literally, so you can't retrieve it, but it's buried out of the way. It's put out of the way in a sealed cave somewhere. And then what they'll do is they'll then release that. The cooling ponds, they'll filter out as much of the sludge and things that they can possibly do that with, chemical techniques to actually bring it out. And then the water itself tends to be very low radioactive levels, so they just release it and it's diffused out into the sea, because they're all basically on incredibly large rivers or on the coast, which is where they do it. Why? Because they need a lot of water. Radioactive power stations, nuclear power stations are highly energetic, so you need a lot of water to take that away. So these ones, they're literally just tens of years. When you've done that, then it's literally just, I'll just make it more clear, for contaminated. Because it's usually low level stuff, and it's quite safe after a while. If it's just been irradiated, they'll store it, they'll leave it for a short time, they'll test it, and then probably just go into recycled into landfill or something like that. Okay, so dealt with in a normal way of dealing with rubbish that we have in this country. So radioactive waste is more about that background, more about that understanding of what's going on. Okay, what I've got is, and we'll finish off now. Go through the workbook. Okay, it's fairly straightforwardish stuff. So use that. Put those things in, those descriptions in particular. Just clarify in your head what they are. On the back, A lot of people have found this as a useful resource. So, just again, a reminder with a couple of key points. What's going on? Here's our heat exchanger. Why? Pure, water, pure non-corrosive if possible. And this is your secondary coolant that goes off to your turbines, etc. What do we got? That's our moderator. Our fuel rods are in the middle. The control rods go up and down. Know your way around it. Waste treatment, again, just kind of key things. What's happening in it? It's being processed. Here's your cooling tanks. Here's your filter to take stuff out so they can process it. That kind of idea. So just, simplest stuff. This one has a reactor in, but just be wary. That's because of the photo I've managed to get a hold of, or the image I used to get a hold of. But crucially, also at the back, and I'll give this out, make sure you get it, there's a really nice grid, three-sided, brings in everything that links stuff together. So the nucleus itself, what do we mean by radioactive ones? You might want to Wikipedia that one. Stability, why are big nuclei more unstable, etc. Half-life idea, the binding energy, which we covered in the first part of this chapter, and just a little bit about nuclear generation. There's not a lot there. This is basically, other than the calculations, all that you need to know for radioactivity and nuclear energy and nuclear structure. Okay. The only point I want to finish with is, again, remind you this topic was nuclear energy. It's not radioactive energy, it's nuclear. So it's energy from the nucleus, because it does not happen naturally. We are inducing that reaction to happen. So most of that chapter, other than the binding energy stuff, most of the chapter, the nuclear power station, the reactor stuff, it's about man-made induction. Radioactivity is that spontaneous and random radiation that comes out from every material that we know of, okay, in all background areas around us. Right, guys, that is everything to do with the nucleus, nuclear structure, and radioactivity. So 3 chapters, a big area, but as I said, the learning summary, I think, makes clear everything that you really need to know. Okay, thanks very much.